Hello, so today we're going to continue our lesson from previous class, which is today we're going to focus on the application of PDE, which has two parts. Okay, so this first one is we are going to focus more in heat. Okay, heat equation. So let's see if we have a root, okay, that have a length L. Okay, so the heat is going to start from here. Okay, when the x equals to 0 and t is the time when the heating started. Okay, and the heat is going to be distributed along the root in a waveform. Okay, and at the end of the root, so the equation going to be the length of the root until a certain time. Okay, ULT. Okay, and in the middle we have another boundary condition, which is u at 0, which is the time now is a 0, but it depends on the x. Okay, the distribution, which is equals to any function of x. Okay, sorry about that. Okay, this is the general equation of heats. Okay, we have a du dt on the left hand side, and then equals to c squared d squared u dx square, which is there is a double partial differential equation on the right hand side. Okay, for the c squared is a constant, which the equation can give any value for the c. Okay, let's see. I'm going to show you. Okay, the example 6, which the question is like this. The equation is du dt equals to 4 d squared u dx square, which means we have the value for the constant, which is 4, or c is equals to 2. Okay, so the heat equation is depends on the three boundary condition, 1, 2, and 3. Okay, which is in the equation we know that L is 2. Okay, so the first one is when the starting of the root. Here u0t equals to 0. Okay, the second one is u2t is equals to 0, and the third one is u at 0 is equals to 100. Okay, the function is not normally in terms of x. It can be a function, a constant. Okay, in this case, the function is a constant of 100. Okay, let's see how we want to solve this heat equation. Okay, first step, we need to assume the solution for UST is equals to x times t. So this is also the same step as the previous example. Okay, so we're still going to use the assumption. Okay, second one, we're going to differentiate it. Okay, with respect to du dt, because in the heat equation we have the du dt on the left hand side. Okay, so we need that. And also for du dx, we need a double differentiation, because there is a double differential on the right hand side. Okay, so we're going to get x double prime t. Okay, then after that we're going to replace it in the equation. Okay, which is in the equation given in the equation. So x t prime, okay, du dt is equals to x dw x dx square x double prime t. Okay, so this is the equation after we replace it with our assumption. Okay, then we're going to do the SOV, which is separation of variables. Okay, now we're going to separate it, t with t and x with x. Okay, so let the prime on the up and the not prime on the denominators. Okay, then after we separate it, we're going to let this equation with a constant. Okay, so for this equation, we're going to let this one is equals to negative lambda squared. So we get the eigenvalue function. Okay, then we're gonna focus on the t first. Okay, this one. Okay, so for the t hand side, we're going to separate it. Okay, t equals to negative lambda squared, and then this is all algebra. Okay, we bring the t on the right hand side, and then we bring it to the left hand side, and then this is the phase when we change it into the auxiliary form. Okay, m plus lambda squared equals to 0, then we will get the roots for m is negative lambda squared, which is given the solution for this t is a, which is a constant, exponent negative lambda squared t. Okay, a is any constant. Okay, this is can be obtained from the second ODE, but it's a little bit different, as in second ODE it's a plus bx, but this one we just going to take a exponent negative lambda squared t. Okay, please don't get confused with second order. Okay, for the x part, right, this one is a little bit longer, so same, we're going to do the algebra. Okay, we move the x on the right hand side, and then we move to the left hand side, and we reduce it into the auxiliary form. Okay, until we get the roots for this one is going to be m equals to 0 plus minus lambda over 2i. So it's a complex roots. So from the second order, you get the x equals to b sine lambda over 2x plus c cos lambda over 2x. Okay, because the solution that we assumed earlier on the step one is u equals to xt, so we're going to use that. Okay, u equals to xt, so x prime time t. Okay, we get x function, the solution earlier. Okay, times with t. Okay, for this one we're going to multiple the constant with another constant, so the constant times with a constant. So constant can be another constant, which means bring us to the final solution that we will get, that which is u xt equals to d sine lambda over 2x plus e, okay, cos lambda over 2x exponent. So no more constant outside because we already times it. So b become d and e become c become e, which is d is b times e and e is c times e. Okay, this is not over yet, as we have 1, 2, 3 more constant to find. So we are going to apply, which is bring us to step 7. Okay, apply all the boundary condition given in the questions. Okay, to find those 3 constants. Okay, we start with the first one. Okay, this one u0 t equals to 0. Okay, from the above equation, okay, we're going to apply it. Okay, so u0 t, so that means x is 0 and t is still t. Okay, so sine 0 is 0, cos 0 is 1, so no more d. So the equation becomes e exponent negative lambda squared t equals to 0. Okay, for this part, you have to take one of this variable to be 0. Okay, exponent negative lambda squared t cannot be 0, as there is no value for non-zero, so it does not exist. So we let e equals to 0. Okay, then after get the value for the constant, we're going to update our equation. Okay, which this one. Okay, so no more e, so only left with d sine lambda over 2x exponent negative lambda squared t. Okay, then we're going to apply the second boundary condition, but don't forget to always update your equation after apply the boundary condition. That's a very important note there. Okay, the second boundary condition is this one, u2t equals to 0 when the x is at the end of the root. Okay, now we put it in the equation u2t, so x is equals to 2 now, so 2 and 2 can be cancelled out, so the equation become d sine lambda, okay, exponent negative lambda squared t equals to 0. As usual, we have to pick one to become 0. Okay, and this one cannot be 0 because non-zero have no value. Okay, we cannot make d equals to 0, then all the solution don't seems it's going to be pointless. Okay, the one that left is sin lambda, so we're going to take this one as a 0. Okay, when sin lambda equals to 0, okay, that means lambda is equals to sin inverse 0, but sin inverse 0 is not 0. Okay, unless you trust your calculator so much, but it's wrong. Okay, it's a 0, but it's also an n pi. Okay, if it has to depends on the sine graph, okay, which I already sketched it here. Okay, this is a Fourier function. Okay, periodically and repeated until infinite. Okay, if you notice in the sine graph, every time the value of x, okay, reach pi, 2 pi, 3 pi, or until certain value of pi, the value for sine we will get 0. Okay, or fx we will get 0. So even though sine 0 is 0, but it's only 1, so we're going to take the rest of not the starting point, the rest of the point, which is n pi. Okay, so sine inverse 0 is n pi. Okay, you need to note that sine n pi is always 0. Okay, that another side note. Okay, so every time sine hit 0, pi, it's always a 0. Okay, so we got the value for lambda, which is n pi. So we're going to replace it in our equation, and now it becomes summation because it's Fourier. Okay, so now we have a summation n equals to 1. It has to start with 1 because n equals to 0 is 0. It's not pi. Okay, until infinity. Okay, d sine n pi over 2. Okay, now the lambda become n pi. X as only negative n pi squared t. Okay, so this is our latest equation, but it's not over yet since we still have another one constant, which is d. Okay, that is when we apply the last boundary condition. Okay, the last one, which is a function k u at 0 equals to 100. Okay, now we're going to apply in this latest equation. So now exponent t is 0. Okay, x has a value, so summation is still there. D sine n pi lambda n pi over 2x still there. Okay, because x is x. Okay, the only 0 is t, so exponent 0 is 1, which is equal to 100. Okay, to get the value d, we cannot just simplify, do the algebra, as it's a summation of Fourier, so we have to solve it by using the Fourier series. Okay. Okay, so by Fourier series, this is a formula for you to find the value of the constant. Okay, so 2 over L, which is the length of the root, 0 until L. Fx function given in the equation. This is whatever function that you get on the left. Okay, integrate with respect to x dx. Okay, so fx in our equation is 100, so we're going to integrate that. Okay, so our L is 2, 0 until 2, 100 sine n pi x over 2 dx. Okay, by using direct integration, we're going to get 100 negative 2 over n pi cos n pi over 2 x. Okay, now we're going to put in the limit value 0 until 2 first. Okay, when you put 2, so the x is cancelled out, so it become n pi. Okay, and then the second one is 0, so cos 0 here. Okay, we can simplify this. Okay, cos 0 is 1, so this one is 2 over n pi minus 2 over n pi cos n pi. Okay, this is the value of d. Okay, we can also factorize it to n pi because same. Okay, finally we get the solution for our example in terms of this. Okay, so this is our final solution. Right, So summation UST equals to find summation n equals to 1 until infinity 200 over n pi 1 minus cos n pi k sin n pi over 2x exponent n pi squared times t. Alright, that's all for today.